Okay, so the topic of this video is the genetics inheritance pattern known as sex-linked inheritance. So let's get started. Well, here's our fictional Henderson family, and in my class a few days ago we met Joshua, little baby Joshua, who was diagnosed with PKU, which is an autosomal recessive disorder. Then we met Maria's side of the family. And we met Maria's siblings, Lucas and Martin, and their dad, Kevin and Mia. And we learned, sadly, that Kevin and Lucas have been diagnosed with Huntington's disease, which is an autosomal dominant disorder. Now we're going to expand the family even further. There's a baby in the oven. Martin and Andrea are newlyweds. So there's Martin, and let's meet Andrea. They're newlyweds, so they've just been married. And Andrea has recently taken a pregnancy test and discovered that she is pregnant. Now, when you don't know the gender of the baby, you tend to just kind of do this diamond symbol. Maybe it's a boy, maybe it's a girl. But she's worried that her baby might actually inherit a disorder known as hemophilia. And she's worried because her father, Andrea's father, is a hemophiliac. He suffers from the disorder hemophilia, and she herself is a carrier of the disorder hemophilia. So let's talk about this disorder. When it comes to sex determination, here's our doctor, and gender, a person's gender is determined by genes that are found on the X and the Y chromosome. Here's a karyotype. Notice how this is a karyotype showing the XX chromosome combination. And women will produce an egg cell when they're mature, sexually mature, and able to have children. They'll produce an egg cell with either with a X chromosome in that egg cell. And so women will always pass along an X chromosome to their children. Well, here's a karyotype showing an XY chromosome. This is a male karyotype. Now, when it comes to males, and when males are old enough to produce sperm cells, males will produce half and half. About half of the sperm cells produced by a male will contain an X chromosome, and the other half will contain a Y chromosome. And so men sometimes pass along their X chromosome, and when they do, they'll produce a daughter. But when they pass along their Y chromosome, that's how they produce a son. And we can say that there is a 50-50 chance of a child being born a boy or girl. And we can prove that in this Punnett Square. Let's do a Punnett Square to help determine the gender of children. Here is the XX chromosome combination for a woman. Here is the XY chromosome combination for a man. When we fill in this Punnett Square, you can see that the odds really do come down to 50-50 odds. There is a 50% chance that the child will be born with the XX chromosome combination and therefore be a girl. And there's a 50% chance they'll be born with the XY chromosome combination and therefore be a boy. Well, let's come to our story here. Our doctor is meeting with Martin and Andrea because she's concerned about their unborn child having the disorder hemophilia. And she says, you know, my dad is a hemophiliac. So let's add her mom and dad to this story. If he's a hemophiliac, I'm going to color in his square. And she says she's a carrier. So what I'm going to do is I'm going to partially color in her circle to imply that she is a carrier. She's heterozygous. And the doctor says, you know, hemophilia is a sex-linked disorder. Let's catch Martin up on the genetics. Clearly, Andrea already understands the genetics, but Martin's probably a little unsure of what this means. So here's our karyotype. And recall that chromosomes 1 through 22, these are the autosomes. These are chromosomes that do not possess genes on them to influence one's gender. PKU, Huntington's disease, these are examples of autosomal disorders. And if you're in my class, we've already learned these disorders. But what we're learning today focuses on the sex chromosomes. The gene that causes hemophilia is located on the X chromosome, and that's why we call hemophilia an example of a sex-linked disorder. It's linked to one of the sex chromosomes. And so that's what a sex-linked disorder is. It's an inherited condition that's found on one of the sex chromosomes. They usually tend to be recessive, and yes, there are some dominant sex-linked disorder, but we're focusing on the most common examples. So they're usually recessive. And you know from my previous examples that I like to use the letter H, capital H for healthy, because healthy is dominant, and lowercase h for the disorder. Now in this case, let's focus on women first. The XX chromosome combination is the combination for a female. And when it comes to the XX chromosome combination, notice I've attached a superscript, capital H, onto each of these X chromosomes. This is homozygous dominant, and it would result in a woman that's healthy. They would not have these disorders. Or a woman can be heterozygous. She can inherit one dominant allele on one of her X chromosomes and a recessive allele on her other X chromosome. She'd still be healthy, but we'd call her a carrier. In our cartoon story, this is Andrea. She said she's a carrier. And then a woman could be, it's rare for women to have these disorders, but it can happen. A woman can possess not one X chromosome with the recessive allele, but two. That's the only way women can have these disorders. But in men, it's a little different. Men, you know, males have the X and Y chromosome combination. So that means on the X chromosome, if there's a dominant capital H allele, the man will be healthy and not have the disorder. But if the man's X chromosome has the recessive allele, they will have the disorder. Now you might be wondering, well, what about the Y chromosome? Does that kind of provide any protection? And the answer is no, because hemophilia, which is the one we're examining today, this is a disorder found on the X chromosome. And so even though a man has a Y chromosome, the Y chromosome doesn't really offer any protection or backup or anything. And so men, our doctor says men are most commonly affected by sex-linked disorders because these are usually found on the X chromosome. And they're rare in women. It can happen. It's not completely unheard of. But these disorders tend to be rare in women. Women have a second X chromosome, a backup X chromosome. And so if one of their X chromosomes has the recessive allele on it, there's a good chance their other X chromosome will have the dominant healthy allele, and therefore they'll be healthy. They'll be a carrier, but they won't have the disorder. Now, if we look at this karyotype here, and if we zoom on into the X and the Y chromosome, let's talk about some examples. Examples of what we call X-linked disorder. These are disorders that are located, the gene has been located on the X chromosome. One of them would be color blindness. Color blindness, the gene responsible has been found on the X chromosome. Another example is hemophilia, the story we're looking at today. The gene responsible is on the X chromosome. And there's a type of muscular dystrophy where the gene responsible is on the X chromosome. When it comes to what we call Y-linked disorders, there are a couple examples of this I found as well. I think it's pronounced Sawyer syndrome. I don't know too much about this particular syndrome, but the gene responsible is on the Y chromosome, as is a type of infertility, Y chromosome infertility. The gene responsible is on the Y chromosome. So these would only affect men because only males have Y chromosomes. But let's focus just on hemophilia today, since that's kind of the disorder facing this family. So if we come back to our cartoon family here, I know that Andrea's dad is a male, so I can give him the XY chromosome combination. I know Andrea's mom is a woman, so I can give her the XX combination. Andrea is a woman, so I can give her the XX chromosome combination. And Martin's a man, so I can give him the XY chromosome combination. And our doctor says, you know, because your dad actually has the disease hemophilia, his genotype must be the X with the lowercase h. That's the only possible genotype of a man that would suffer from these disorders. And so he must have passed on his X with the lowercase h to Andrea, his daughter. We know he didn't pass along the Y chromosome because Andrea's female. Therefore, the dad must have passed along his X chromosome. So Andrea received her dad's X chromosome with the lowercase h. My mother has no history of hemophilia in her family, and so that means when it comes to Andrea's mom, I can label her genotype this, X with capital H for each of them. And so that means that her mom must have passed along an X with a capital dominant H. And that's why Andrea's healthy. She has this backup X chromosome with the capital H on it. So she's fine, she's healthy, she does not have hemophilia, but she's a carrier. And Martin, since you do not suffer from hemophilia, your genotype must be an X with a capital H. That's the only possible combination of a male who does not have this particular disorder. So now that we know Martin and Andrea's genotype, we can set up a Punnett square for them. There's the genotype of Martin, there's the genotype of Andrea. And when we fill in this Punnett square, not only can we tell if they're going to be healthy or have a disorder, but we can also identify their gender. XX chromosome combination is a female, and because there's capital H's, we know that that female will be healthy. XX chromosome combination is a female, and a capital H with a lowercase h means that the person will be healthy but a carrier. Now here's the XY chromosome combination, but there's a capital H there, so I know it's going to be a male who's healthy. And here's the X and Y chromosome combination, but there's a lowercase h, so here's a boy who would suffer from the disorder hemophilia. And so our doctor says you can see there's a 25% chance that you could have a child with hemophilia, 1 square out of 4. And if the child is a boy, we don't know yet, but if the child is a boy, there is a 50-50 chance that he will suffer from hemophilia. And if the child is a girl, there is a 50-50 chance that she will be a carrier. The good news is, if it's a girl, the child will be healthy regardless. However, the child could be a carrier. And Andrea says, I think we'd like to know the gender of the baby. Well, that's kind of the end of this cartoon family here. But before we're done, I want to do some summary review here. So here's a practice problem. If you're watching, pause the video, read through that sentence right there, and then try to answer these 4 questions. I'm going to go over the answer in 3, 2, 1. Okay, the story says Jen is a healthy carrier of this disorder hemophilia, and Adam has no history in his family. So when I fill in the Punnett square, I can see there's the option of a healthy girl. I can see there's the probability of a healthy boy. There's a probability of a healthy girl who's a carrier. And there's the probability of a boy who has hemophilia. So now look at the 4 questions. Question A, what is the probability they have a daughter with hemophilia? And the answer is 0. They can produce a male, a son, with hemophilia, but not a daughter. Question B, what are the chances they could produce a carrier child? The answer is 1 square out of 4, 25%. What is the chance they could produce a child with hemophilia? The answer is 1 square out of 4, 25%, and that child will be a boy if they have hemophilia. What is the odds of producing 2 healthy children? Now this question's a little trickier. You might think the answer is 75%, 3 squares out of 4, but that's not the right answer. The answer is 9/16 or 56%. Well, how did I get that answer? Let's explain. Here's 2 babies. Pretend they have baby 1 in the year 2015 and pretend they have baby 2 in the year 2018. Well, pretend it's 2015 right now. What are the odds that the baby born in 2015 will be healthy? Look at the Punnett square. There is a 3 out of 4 chance that the baby in 2015 will be healthy. A couple years go by, it's now 2018. Ben and Adam want to have a second child. What is the odds that the child born in 2018 is healthy? Look at the Punnett Square. There is a 3 out of 4 chance that the baby in 2018 is healthy. So how come the answer is not 3/4? Because I have to combine the odds of the two babies. I do that by multiplying together. What's 3 times 3 in the numerator? It's 9. What's 4 times 4 in the denominator? It's 16. That's why the answer is 9/16. Here's another practice problem. Hemophilia is a sex-linked disorder. Pause the video and try to answer these questions and try to draw the pedigree. I'm going to go through the answers in 3, 2, 1. Okay, so there's Kelly. I think Kelly implies a circle. She does not have hemophilia, even though her mother did. Her mother had the disorder, which is rare for women to have these disorders, but it's not impossible. It can happen. Notice how I colored in Kelly's mother. You color in the symbols whenever they have the disorder. And there's Jim. He is a hemophiliac, so I colored in Jim Square. Their first child's name is Barry. I think that implies male, and he's healthy. But their other child, Rachel. Rachel implies a girl. She's a hemophiliac, so I colored in her circle. Again, it's not impossible for women to have sex-linked disorders like this. It's just uncommon. And the question says, draw a pedigree. There's the pedigree. And now let's do a Punnett Square. Well, I can start before I do the Punnett Square. Let me identify the genotypes. Well, if Kelly's mom has a disease, there's her genotype. That's the only combination of a woman who has a disease. That's the genotype of Jim. That's the only combination that would produce a man with the disorder. Well, there's Rachel. She must be homozygous recessive because that's the only way to produce a female with the disorder. Well, there's Barry. Barry I know is healthy from the story. The story says Barry is healthy. That's the only possible combination that will produce a man that's healthy. Now, look at Kelly. I know she has an X chromosome with the lowercase h. She must have received that from her mother. Now, the story doesn't really tell me anything about her father, but I know she had to receive an X chromosome from her dad. So clearly, if I can draw a square to symbolize her dad right here, I know that Kelly does not have hemophilia. It says that in the story. So therefore, the dad must be fine. Kelly's dad must not have hemophilia. He must have passed his X with a capital H. Now I can draw a Punnett Square for Jim and Kelly. There's Jim's genotype, and there's Kelly's genotype. When I fill in the Punnett Square, I can see these results right here. Now, I look at the 4 questions. What is the probability of having a healthy son? The answer is 1 square out of 4, 25%. Question B, what's the chance of having a healthy daughter? The answer is 1 square out of 4, 25%. Question C, what is the odds or the probability of having a child with hemophilia? The answer is 2 squares out of 4, or 50%. And question D, what are the chances of having a child who's a carrier? You can see it's 1 square out of 4. And so there you have a practice problem. Now this right here is a real good challenge. Here's a pedigree involving 14 people. Pause the video. Try to identify the genotype of these 14 people. There's a hint. One person in this family, you're not going to be able to determine their genotype. So here we go. Let's go ahead and pause the video. When you're done, let's check our answers. I'm going to go over the answer in 3, 2, 1. I think the easiest way to start is with the squares, the males, because there's only 2 possible genotypes. If the square is colored in, like person 5, 13, and 14, then they have to have the X with the lowercase h. And because they're males, I can add the Y chromosome. Now, I know that the other squares, person 1, 3, 7, 8, 10, and 11, they're squares, so they're males. they have to have the X and Y chromosome combination. And because the squares are not colored in, they're not shaded, they have to be healthy, which means they have the capital H on the X chromosome. So I've already finished a good number of people in this pedigree. So now I want to turn my attention to the circles, the females. There's 3 possible genotypes for the circles, the women. But I can cross out the bottom one because none of the circles are shaded in gray. None of them are colored in, so none of the circles have the disorder. But I have to figure out, are the circles homozygous dominant or heterozygous? And that's where the challenge comes in. Well, every symbol that's left, all the circles are women, and they're not colored in, so they're healthy women. So because they're healthy women, I can go ahead and give them an X with a capital H. I know they have at least one X with a capital H. I'm trying to figure out what's their other X chromosome. Does it have a capital H or a lowercase h? Well, child 5 is going to be a big help. Boy 5, he's a boy, so he must have received the Y chromosome from his dad. If he got the Y chromosome from the dad, then that X chromosome that he has must have come from his mom. And so notice that child 5 allows me to figure out that woman number 2 is a heterozygous carrier. So I can go ahead and color in half of her circle. And we can use that same logic to help us uncover another woman. Look at boy 13. He's a boy. Boy 13 got the Y chromosome from his father, which means boy 13 got the X chromosome from his mother. So we now know that woman 6 also has to be a carrier. Well, we can go ahead and use that same logic to solve another woman. Look at boy 14. Boy 14 is a boy. He got his Y chromosome from his dad, which means boy 14 got his X chromosome from his mom. So I now know woman number 9 has to be a heterozygous carrier. Now, let's try to figure out the other circles. Remember, the hint that I gave you is that one person is unknown, and we don't know person 4 and 12 yet, but we can figure out one of the two. First of all, look at woman number 9. I know she got the X chromosome from her dad. That's why she's a woman. So she received an X with a capital H from her father. So where did woman 9, look at woman 9. Where did her X with the lowercase h come from? That had to come from the mom. And so I now know that woman 4 has to have an X with a lowercase h. She has to be a carrier. Now, my dilemma now is woman 12. I know she's going to receive an X with a capital H from her dad. That I know. She's going to get an X with a capital H from the dad. The problem with woman 12 is, what does she get from the mom? I don't know. There's a 50% chance that she receives an X with a capital H from her mom. There's a 50% chance that she receives an X with a lowercase h from her mom. So that's the one person whose genotype we just don't know. And there you go. If you're in my class, pause the video and try to answer these 5 questions, and I'm happy to check your answers before school or after school one day. Hope you found this video helpful. Thanks for watching.